So we've defined the quotient ring R mod I. We've seen an example. We'll see some more examples in a little bit. But we've defined the quotient ring R mod I, and it comes from a ring R and an ideal I of R. Now, a natural question is, how does the original ring and the quotient ring relate to each other? They relate with the following theorem. So we're going to define a function phi from the original ring to the quotient ring. And it's going to be the function that takes an R to its corresponding coset. It's the you go to your coset function. Then phi is an epimorphism. And the kernel of phi is exactly I. Proof. Start with an epimorphism. It firstly needs to be a homomorphism. We check. Phi is a homomorphism. All right, it needs to send 1 to 1. So let's go preserves 1 first. Phi of 1, by definition of phi, is you go to your coset. And that is the multiplicative identity in R mod I. So it preserves 1. It needs to preserve plus. That is, phi of R1 plus R2 should be equal to phi of R1 plus phi of R2. So again, this is something we need to check. It's not something that's obvious. We just write equals and we're done. No, we have to check. So phi sends R1 plus R2 to its coset. Phi of R1 is going to be the coset of R1, and R2 is the coset of R2. So are these things the same? Well, yeah, this is exactly how we defined addition, and we had to show it was well defined. So we actually already went through the proof that this works. Similarly, we need to show that phi is compatible. Oh, that phi got away from me. Phi is compatible with multiplication, preserves multiplication. So on the left-hand side, we have to send R1 times R2 to the coset R1 times R2 plus I. And on the right-hand side, R1 goes to R1 plus I, and R2 goes to R2 plus I. So this is a question, and we want to know, are these equal? Well, yeah, these are equal. This is how we define multiplication. We actually defined the operations on R mod I in kind of the only way possible, and we've also defined it in such a way that this function that we've constructed here becomes a homomorphism. So we sort of built in to R mod I that this is a homomorphism. All right, so we conclude that phi is a homomorphism. Now we have to check that it is an epimorphism, that is, it is onto. So to see it's onto, we have to take any element of the codomain. Oops, take some R plus I in R mod I. And we have to show that that comes from something in R. Well, phi of R is R plus I. What should it come from? It should come from a representative R. And so this tells us then that phi is onto, because every element in the codomain comes from something and is therefore an epimorphism. Cool, so it is an epimorphism. It's a big old check mark there, there, and there. And the last thing that we had to check is that the kernel of phi is I. So let's do that now. Let's take some I in I. And then phi of I is I plus I. But I is an element of I, so it gets absorbed into I. So I is in the kernel. Now let's take let's see, R in the kernel of phi. We need to show R is in I to complete our double containment argument. Well, then 0 plus I is phi of r, but because it's in the kernel, but it's also r plus I. So this tells us then that r minus 0 is an element of I, or equivalently, that r is in I. So we've shown that if you're in the ideal I, you're in the kernel, and if you're in the kernel, then you're in the ideal. So that's our double containment argument. So we conclude that I is equal to R. All right, so let's go back up to the theorem real quick. What this theorem is telling you is that any ideal is the kernel of a epimorphism, in particular a homomorphism, and it's the kernel of a very particular one. It's the kernel of the one from R to R mod I. That doesn't mean it's not a kernel of another homomorphism, but you can always express an ideal as a kernel. And we saw also that all kernels are also ideals. So what this theorem tells us is it tells us that the notions of kernel and ideal are the same. And I'm going to put the same in quotes because it's not quite true, because the kernel refers to a very particular homomorphism. You have the homomorphism already given to you. Ideals don't necessarily refer to a particular homomorphism. They're just a subset of R. Ideals, the same ideal can be the kernel of many, many, many homomorphisms, many different ones with different codomains and different things. So it's not like they're the same necessarily, because there is a difference between them. In particular, the kernel itself, this already has a homomorphism as part of the data of giving a kernel, whereas this guy does not have a homomorphism. One explicitly given. This one has a homomorphism explicitly given. But what this theorem is telling us is the subsets that we get from ideals and the subsets that we get from kernels are the same subsets.